In the previous lecture, we discussed the basics of wireless communication. In this lecture, we are going to look into the IoT device architecture and a particular platform that we are going to use extensively in this course. Let's examine the significant components and the tasks of IoT devices. These include computation and storage, sensing and actuation, power management, and wireless capabilities. In this course, we will delve deeper into each of these tasks with a particular focus on the wireless connectivity or wireless networking. So let's quickly look into what each of these tasks are. Sensor allows IoT devices to interpret and understand the physical world around them. These include, for example, sensors to measure temperature, humidity, or cameras that allow these devices to see the physical world. Actuators can influence the world, including, for example, LED that shines light, or motors that could allow robots to move in the environment. Microcontrollers allow these devices to make sense of the sensor reading or also control these actuators, store information, and also interface with the wireless radios that allow these devices to support wireless connectivity. Power management is another critical aspect of IoT devices, and this involves powering the various components that we have just talked about. It also includes circuitry for managing storage devices, and for some IoT devices, it could also include harvesting energy from the ambient environment so that these devices could operate without batteries, only on the energy that is harvested from the environment. Wireless capabilities, including the support for standards such as Wi-Fi, Bluetooth, or Zigbee, is also crucial to IoT devices, as they allow these IoT devices to communicate with each other as well as to our devices such as mobile phone. So most IoT devices have a pipeline architecture, and this is very similar to the one that we depict in this slide. In this architecture, the sensor readings are passed through a series of stages where they undergo pre-processing before being wirelessly transmitted by a radio transmitter. And of all these stages in the pipeline, the radio transmission is the most power-intensive task, while sensing is the least power-intensive task. So today we are going to delve deeper into one of the key stages of IoT devices, which is processing. And at the heart of these IoT devices is something that we call microcontroller. So what are microcontrollers? These are small computers that are integrated into a single circuit. It comprises typically a central processing unit and various peripherals, such as communication interfaces and different types of memory. So these peripherals work together with the central processing unit to enable the microcontroller to interact with other devices and perform its tasks. So what is the difference between a microprocessor and a microcontroller? Microprocessors are found in our computers. They are typically considered a computer on chip, and you can consider them to be typically a CPU with only pins. So microprocessors lack these peripherals that microcontroller has. Therefore, one way to differentiate between the two is that microcontroller can be thought of as a microprocessor with various peripherals devices that are built into one single circuit. On the slide, we show a very historic microprocessor from Intel that sparked off personal computer revolution many decades back, and this is Intel 8088. So system on chip is another type of evolution of a microcontroller and can be found in most IoT devices and smartphone. A system on chip is a microcontroller with extensive additional peripheral capabilities and features such as radio transceivers, machine learning accelerators, and multiple chips integrated into a single design. In recent years, there has been also a significant interest in the development of low power accelerator chipsets, and these chips are designed for specific tasks such as speech detection. As an example, the NDP-120 that we show on the slide enables detections of simple words at under 100 microwatts of power consumption. And this power consumption is orders of magnitude lower than typical processors or a system on chip that are used in smartphone and other such devices. So next we are going to talk about sensortag platform. This platform we are going to use extensively in individual assignments and the projects in this course. So the core of the sensortag platform is a Cortex-M3 microcontroller, which operates at the maximum clock rate of about 48 megahertz. It features various types of memory, including flash, which is used to store the program, SRAM, which stores variable and other temporary information from the program. Additionally, the platform supports wireless connectivity through Bluetooth and Zigbee wireless standards. Thus, it has these radios to support these wireless standards. Furthermore, this platform is equipped with 10 different kinds of sensors, allowing this device to perceive the physical world. These sensors include allowing you to record speech, look into the magnetic readings, temperature, and other such type of information. So here we show the block diagram of the CC265 wireless MCU, which is at the heart of this device. We have already talked about the Cortex-M3 core. It also has, for example, other peripherals like, for example, UART that can allow these devices to communicate to your computer or another microcontroller, or things like, for example, the AES block, which allows it to encrypt information, or RTC, which allows it to keep track of timing, or power management block like DC to DC converter. So the RF core comprise of circuitry to allow you to generate this radio waves, which can then be transmitted from this sensortag device. So I would highly encourage you to look into the data sheet of this microcontroller or a system on chip, and we have linked it onto the course homepage. So this is how the device looks. It's just slightly larger than the coin cell. And this figure demonstrates the various sensors that are present on this device. It includes, for example, pressure sensor. It includes light sensor, humidity sensor, and motion sensor that allows it to keep track of acceleration or motion in the three different axes. It also has an antenna, but it has a PCB antenna. So this antenna is just printed on the board itself. So you don't have this big external antenna that is connected to this device. Finally, we also show the backside of this platform. It has things like buzzer that can allow you to sort of like make noise if you want. And then it has also microphone that can allow you to record speech, and the JTAG or programming interface is where you would connect another device called a debugger to this sensortag platform. And this debugger allows this device to or to program the sensortag and put your custom code on this device. And while you can power this device through USB when you have connected it through a debugger, but if you want, you could also disconnect the debugger once you have programmed the device and power this sensortag using only a coin cell battery. So this concludes this part of the lecture. In the final part of the lecture 2, we are going to give you a brief overview of Contiki operating system, which we are going to use on this platform.